All right. Today today we will write down the character table for the group S5. In the last two videos, we have seen several theoretical results on the restriction of a representation to a subgroup of index 2. So as I mentioned there, that now we will use those results in the special situation when G is S5 and H is A5. So from the character table of S5, we will obtain the character table of A5 using the theoretical results that we have seen in last two videos. So the first step towards obtaining the character table of A5 is first getting the character table of S5. So now we shall, in this video, we shall write down the character table of S5. Then using those results, we will obtain the character table for A5. Okay. So let's start. So character table of S5. In order to write down the character table for S5, first we have to find out the conjugacy classes of distinct conjugacy classes in S5. And in S5, thankfully, conjugacy classes correspond to different cycle types. So you have to pick a representative. You have to pick one representative for each cycle type. So let's start with I. I is the identity transform, identity permutation. Then it comes 1, 2, then 3 cycles, then 4 cycles, then 5 cycles, then 2, 2, and then comes 3, 2. Okay. So these are the all possible cycle types. So we have 7 distinct cycle types, and we have chosen one representative from each cycle type. So thus we see all the conjugacy classes here in S5. So let's also write down the sizes of the conjugacy classes. So for identity, it is 1. For 1, 2, it has to be 10 because we can make 5C2 choices. 5C2 is 5 into 4 by 2. So for any 2 choice, we can make a unique 3 cycle. For unique 2 cycle, for 3 cycle, it is 20 because 5C3 is 5 into 4 into 3 by 6. So 5 into 4 into 3 is 60 by 6. So 10. So therefore, we can pick up 3. We can pick up 3 say distinct elements from the set of 1, 2, 3, 1, 2, 3, 4, 5 in 10 ways, and given any collection of 3 elements, from that we can make 2 cycles, 3 cycles. Therefore, the number has to be 20. Similarly, here it will be 30. Here it will be 25. So I leave the verification of these to you. Here it has to be 15 because first of all, in order to get find the number, in order to get a permutation with cycle type 2, first we have to get the fixed point. So the fixed point can be chosen in 5 ways, and then once we have chosen the fixed point, then from the rest, if we want to make the first transposition, that can be made in 2 ways. So 5C2 is 10. So thus it is 5C2 is 10, and then sorry, 5C2 is, yeah, again I'm sorry, 4C, from the 4 we have to choose 2. So 4C2 is 6. But since since the disjoint transposition commute, so the number has to be divided by further half, and so that is 15. And then what we have is this, where it becomes 20. So I just leave the verifications that verifications of the sizes of the conjugacy classes to you. I have just done a few for you. you should be able to do the rest. So thus we have the representatives for each conjugacy classes, and we have the size of the distinct conjugacy classes as well. Now we will write down the characters for S5. So the first character will be the trivial one. Let's denote that by chi1. So it takes one identically everywhere. So everywhere its value is 1. Okay. Next, is there any character with dimension 1? Yes, for permutation group, we have the sign character, which precisely assigns the value 1 to even permutation and -1 to odd permutation. So therefore, the sign character is precisely, the values of the sign character is precisely this: 1 minus 1, 1 minus 1. Again, this is 1, 2, 3, 4. So this is a 1, 1, and -1. Okay, so we have two one-dimensional characters. Let's just see that they are all, because for any finite group G, the number of one-dimensional characters is just the order of the this quotient group. So when G is S5, then G prime has to be A5. So therefore, we have exactly two distinct irreducible distinct one-dimensional characters, and we have already found two. So therefore, we don't have any more. Okay. So now we should look for higher characters with higher dimension. So we will now talk about a character which comes from the permutation character. Let's just write that. So recall that Sn has Sn acts on the set 1, 1 to n, and the action of Sn on this set 1, 2, 3, 4, 5. From this action, we get our representation, which is called permutation representation. This is simply given by each sigma gives rise to the following. Here it will be not just up to 5, it will be to any n. So 1, 2, 3, 4 up to n. So each sigma gives rise to the following linear map in Cn, which is decided by permuting the coordinates. So Z1 up to Zn is being mapped to Z sigma inverse 1 and then Z sigma inverse n. Okay. So for each sigma, corresponding to each sigma, we get this linear map, and that gives us a homomorphism. N-dimensional complex homomorphism of Sn. Okay, this is called the permutation presentation, and let's denote its character by chi. It's easy to see that this representation is not irreducible, because the vector V which stands for E1, E2, En, this vector is invariant is an invariant vector of this representation. Therefore, the sub-representation on the subspace generated by V is a trivial representation of Sn. And furthermore, we see that the matrix of this linear transformation for any sigma with respect to the standard basis is just a permutation matrix. Therefore, the matrices are unitary. Hence, this representation is in fact a unitary representation. And once a unitary representation is there, then the orthogonal complement of any invariant subspace is also invariant. And thus it is easy to see that the orthogonal complement of the subspace generated by V is precisely this one. Though say it consists of those tuples in Cn such that Z1 up to Zn is just 0. Okay. So this is the subspace. So this is a one-dimensional subspace, and this is n minus one-dimensional subspace. So thus Cn admits the decomposition. Cn admits the following decomposition into invariant subspaces. So that forces that pi is nothing but, so the character of this representation, which has to be the trivial one, plus another character. So far, so a priori we do not know whether this is irreducible or not, but the character of this representation, we let us denote that by chi3. So therefore chi3 just becomes chi3 of g, that just becomes that pi of g minus 1. And what is pi of g? For any action, the character of the permutation representation is just basically the number of points which are fixed by g. Well, so here we are actually using the notation sigma. So a number of points fixed by sigma, and so that minus 1. So this is what we know for this character chi3. So with this formula, let us compute the values of the character chi3. So the values of the chi3 is the following, that here in case of identity, it has 5 fixed points to so the value here will be 4. So here it has to be 2, here it will be 1, for here it has to be 0, here it has to be minus 1, 0, and 1. Okay. So thus we have found the characters, we have found the values of the characters chi3. But the question that remains is whether this has its place in the character table or not, or in other words, whether this is irreducible or not. Let's just check that. In order to show whether this is irreducible or not, what we do is we consider the inner product of chi3 with itself, and that can be easily seen to be the following. That the first one comes to be 4 square by 120, right? These are just from the definition. Then what we get is 2 square by 16. Okay, 2 square by 12 it is. And then it comes that 1 by so here 1 by 6. Then we don't have anything for this or for these two zeros, therefore we only have this and that. So this is minus 1 square by 6, and finally we get 1 square by so minus 1 square by 6, and minus 1 square by 6. I think I made a small mistake. Yeah, so here it is minus 1, so minus 1 by 5. So for well, I think I just interchange. So for this it will be minus 1 square by 5, and there it will be 6, minus 1 square by 6. So if you make the computation, it turns out to be 1. So thus chi3 is an irreducible character of S5. Okay, once that is clear, so we have seen that chi3 is chi3 is just chi3 is irreducible character. So and the dimension of chi3 is 4. So thus we have found three characters, 2 1-dimensional, another 4-dimensional. We still have to find 4 more characters. Okay, the fourth character is, can be found in the following way, that we have this chi. So we have chi2 and chi3, right? So we have already seen that for any character chi, for any one-dimensional character, for any one-dimensional character lambda and a representation rho, this is also going to be a representation of the same dimension, and this is irreducible provided rho is irreducible and its character is just lambda times the character of rho. This is what we have seen earlier. So therefore so thus this is an irreducible character that we get for this S3. For this S5, let's now compute its values. So the value will be just pointwise product. So let's call this character as chi4. So therefore we have so let's write, so we have this chi4. So again, let me remind you that chi4 is just the product of chi2 and chi3, and it is now you can immediately see that the value of that is just 4 minus 2 1 0 minus 1 0 and 1. Okay, So this is another character which is different from the earlier one. So this indeed another distinct, another this is another different, another irreducible character which is different from the previous ones. So thus we have 4 irreducible characters. Okay. So we now have to find 3 more characters. All right. So how to find the last 3 characters? That is, for that we will recall the symmetric square and alternating square, symmetric square, alternating square of our representation. So what we do is, let us take chi as the chi3, and then we recall that the symmetric square character is precisely given by this chi g square plus chi of g square, right? Similarly, we have a formula for chi alpha square where this is plus is replaced by -1, but in once we once we know the symmetric square character, from that we can easily compute the alternating square character by using this relation. So it just shows that chi g square is nothing but sorry, chi g square is nothing but symmetric. Just a minute. So so alpha square g is nothing but chi g square minus chi square g. All right. Yeah. So using these 2 formulas, since we know the values for chi in our case, so using these formulas, first I can compute the values of the characters of symmetric square, and if you make the computation, then you will see that the values of the symmetric square is precisely going to be the following. The reason for using a different color will be apparent shortly. So using this formula, if you compute the values of the symmetric square character, this is what you will get. So I leave the computations to you. I won't perform it here. I'm just so you just have to you just have to substitute the values of these into the formula and compute that. So once you have done that, this is what you are going to get: 0, 1, -1, and 0 and 1. Okay, so this is what you are going to get for this symmetric square. And then then you do have the character values of the characters for the alternating square, and that is precisely going to be the following because of this relation. So for example, the square of this has to be the sum of this and that. So here you must have 6. So similarly here you have to have 0, 0, again a 0, 1, -2, and 0, right? 1, -2, and 0. Just a minute. Yes, sorry. Yeah. So 1 minute. Yeah, that's fine. I hope that I haven't made any mistake so far. 1, 0, 0, exactly. 0, 0, exactly. So yeah. So this is our chi3, and from that we have to find out 110. So okay. See here, this will be simply 0. Yeah. So just a minute. I think we are just finding x chi alpha square. So this is 60001 minus 20. Yeah, that seems to be fine now. So therefore, yeah, so thus we have computed the character symmetrical alternating square characters. So the natural question that comes out at this point is whether it is legitimate to whether it is legitimate to keep that in the in this list or not. And yeah, whether it is legitimate to keep that in this list, in this character table or not, or in other words, whether these characters are whether these characters are irreducible or not. So for that, again, we will do that inner product checking. That is, first let's see that what happens to x alpha square and x alpha square, what happens to the inner product. And once you make the inner product, so what is the inner product? So this is just 36 by 120. So this is 36 by 120. Then the next term is just then the next term is just 1 by next term is 1 by 5, 1 by 5, and the rest term is 4 by 8, and that clearly happens to be 1, which shows that it is simply, which shows that this chi alpha square is an irreducible character. So it indeed has the place in the character table. So thus we have found a different character. Sorry. So we have found, thus we have found a different character in the character table. So let's just relabel that with a notation. Let me just write it by chi 5. So thus we have we have found a six-dimensional character of six-dimensional character of yeah, six-dimensional character of the group S5. Okay, so far so good. So far so good. I hope that there is no mistake in what we have seen so far. Just let me make sure for a moment. Minus 1, 0, 1. Yes, yes, yes. I think that is now fine. Yeah, that is now fine. Okay, okay. So yeah, so the fifth one we have already found out. Now let's see that yeah, so but this is a alternating square character is already, we have just seen that it's a irreducible character. So the question remains that what happens to this symmetric square one, this character. So for that we will again, we will make the same checking once again. So what happens to the symmetric square character? So if you just simply check, it happens to be well, there's a small mistake here. The small mistake is 0 0. Just a minute. 0 0. Yeah, there's a very small mistake here. So value of this is just here. This and these are wrong. So here it will be 4 1 and then square 0 0 2 1. Yeah. Now the sum of these two becomes 0. Okay, fine. Now it is fine. Okay, so let's now make the computation. So it just shows that 100 by 120. So yeah, so once 100 by 120, and next term is 16 by 12, 16 by 12. The third term is 1 by 1 by 6, 1 by 6. That next term is 4 by 8. This corresponds to that. So this is 4 by 8. Okay, it's just so 16 by 20. Yes, 16 by 12, and then again it comes is 1 by 1 by 6, because these are the order of the centralizer of the element. And then finally for this 2, what you have is 2 by so 2 square by 8. Okay, so if you now calculate that, it happens to be 3. So therefore this is not going to be an irreducible character of S5, but however this indeed gives us an irreducible character in the following. So as I'm saying, that this indeed gives us an irreducible character different from chi1 up to chi5 as follows. That if you just compute rho sigma square rho 1, so what you thus get is, if you just make the computation, 10 by 120. The next term is 4 by 12. Next it is just 1 by 6. Next it is just 2 by 8, and then 1 by 6. This happens to be 1. And then similarly x sigma square chi 3, that is also easy to see that the first term is just 40 by 120, then 8 by 12, then 8 by 12, then 1 by 6, then minus 1 by 6. It also happens to be 1. So thus we see that though chi sigma squared is not an irreducible representation, but indeed, so since it is not an irreducible representation, it will be the sum of a few irreducible. So since this is not an irreducible character, so it will be the sum of a few irreducible characters. So in that, so chi1 is there, because the trivial representation occurs in the symmetric square representation exactly once. So for this representation whose character is chi3, and then there will be something, we just have to determine we will determine what we have here. So recall that for any character chi, if chi is just for any group G, finite group G, suppose any character chi is just the direct sum of the sum of chi1 up to chi k with multiplicity n1 up to nk, and n1 up to nk and chi1 up to chi k are distinct irreducible characters of G. Then if this happens, then what is then chi is nothing but the summation of ni square. Okay, the sum of the square of the multiplicities. Okay, so this holds in general for any finite group G, for any G. So if you use this here, so here chi sigma, so here this is nothing but the sum of the square of the multiplicities, and here are already two characters with multiplicity 1 1, and here you have the sum is 3. So therefore it shows that here there will be exactly one character with multiplicity. There is exactly one character with multiplicity 1, because then only 1 plus 1 plus 1 will be 3. So thus it shows that we have a character, we have an irreducible character here. So let's call that chi 6. Let's call that chi 6. So chi 6 is defined as chi sigma square minus chi 1 minus chi 3. So this is how chi 6 is defined. So we have a character here whose dimension is easily seen to be 5, because here the dimension is 10. Here the dimension is 10. this has dimension 1, this has dimension 4, so then this has to have dimension 5. So thus we have got irreducible character of dimension 5, whose values can be obtained by this. This character is certainly different from what we have found earlier, because earlier none of the characters that we have found, none of them had dimension 5. So as I said, that though this character of the symmetric square is not an irreducible, but that indeed contains a irreducible character, which is different from what we have, which is different from the character that we have found earlier. So this indeed leads us to a different irreducible character, which we denote by phi 6. And let me again just repeat. So since chi sigma square is not an irreducible character, it will be the sum of a few irreducible characters. So therefore we have already checked that chi 1 appears once here, chi 3 appears once there. So therefore there will be some other characters. On the other hand, for any general group, we have seen that if chi 1 up to chi k are distinct characters and they appear ni n1 up to nk times respectively, then this happens to be the sum of ni square. So here, since we know that this is, since we have already computed that this is 3, so therefore 1 plus 1, and then whatever appears here, the sum of the squares of their multiplicities will be 3. So that here we have so yeah, so 1 plus 1, and then the sum of the multiplicity, sum of the squares of the multiplicities of the other characters, we have to be 3. Yes, sorry, yeah, I'm right, that 1 plus 1 plus the rest, sum of the rest has to be 3. Yeah, so that forces that there can be exactly one irreducible character whose multiplicity is 1. So we have denoted that by chi 6, and then it is quite clear to us that chi 6 has dimension 6, dimension 5. So this is a different irreducible character, and the values of chi 6 can be found from the values of chi sigma square, chi 1 and chi 3. So it's a different irreducible character. And let's now, using this formula, let's now compute the values of chi 6. So one can do it easily. So the values of chi 6 is precisely going to be the following. Values of chi 6 is precisely going to be the following. Precisely going to be the following. 5, because it has dimension 5, then 1, minus 1, minus 1, 0, 1, 1. Okay. And once chi 6 is there, then again, like earlier, we will consider chi 2 times chi 6. So it is also going to be an irreducible character, because an irreducible character multiplied by a one-dimensional multiplied by a non-trivial character gives us a different irreducible character. So let's call that chi 7. So thus the values of the chi 7 is just a pointwise product. So here we will simply compute that. So this has also dimension 5. Then we get minus 1, 1, 0, 1, and minus 1. Just you have to just simply take the product chi 2 and chi 6. Minus 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1, 1, 1, 0, 1, 1, and then 1, and then just a minute. Sorry, I have written chi 2 has to be minus 1 because it's an odd permutation. So thus we get the complete character. So we will now remove that because this is no longer irreducible, but we wrote that because it was necessary in view. So with the help of this chi sigma square, we computed the value of the alternating square character, and then from chi sigma square, though it is not an irreducible character, but however this is not too useless. This contains another irreducible character which we were looking for. So and because chi inside the chi sigma square, chi1 appears 1, chi3 appears 1, and since the inner product of this itself with itself was 3, so there will be exactly one irreducible character different from exactly one irreducible character with multiplicity 1. So I've denoted that by chi6. So chi6, the values of chi6 from the obtained can be obtained from this formula, and we easily see that its dimension is 5. So it's a different character. So we place that here. So once we have found chi6, from that just multiplying by chi2, we get chi7. Thus we have all the 7 characters that we are supposed to find. And just also to convince ourselves that things are absolutely okay, we just check the dimension formula. So 1 plus 1 plus 4, 16, 16 to 34, and then 36, 34, 36 is 70, and then 25, 25, 50. So all total we get 120, which is the order of the group. So thus we have made the we have written the character table for the group S5. Please note that while writing the character table in the beginning, some small mistakes happen. For example, by mistake I wrote while writing the symmetric square character, we made a mistake in one entry. So but later on we have corrected that. And then also this was initially written wrong because it's a odd permutation. So but yeah, so once you have corrected that, things are absolutely fine. So this is what the total character table of S5 is. So with this we will so as I said, our main object is to find out the character table of A5 from that of S5 using the theoretical results for restriction of a representation to a normal subgroup of index 2. So we will use those theoretical results to derive the character table for A5 from this, and yeah, from this. So in the next video, we will determine the conjugacy classes of A5, because to write down the character table of A5, first we need to find out the conjugacy classes. In the next video we'll find out the conjugacy classes in A5. Then once we find that, then from this table we will write down the table for A5. So with that I will stop here.